Hello. In this chapter, Flows in Pipes and Ducts, we will be dealing with the energetics of piping systems. So we're not going to introduce much of new information in here, rather than but we're going to expand on a lot of the information we have seen in chapters 3, 4, and 5. So piping systems are everywhere. They're in all types of industrial processes, as you can see in this figure. The air that you breathe goes through the respiratory ducts to your lungs, and the blood that is being pumped from your heart to the organs goes through an intricate and complicated piping systems. Oil gets carried through piping systems in certain air conditioning systems have lots of ducting conduits that carry air from point A to point B to keep you cool or to keep you warm. So the pipe flow problem is an essential problem in fluid mechanics, and it's a very basic problem, and I believe that it has been studied most in fluid mechanics, so it's worth focusing on it as a capstone chapter for our introduction to fluid mechanics course. So in this chapter, all the information that we have learned throughout this semester will come to life, and we will be able to deal with real life problems and systems. So why are we interested in pipes and ducts? And what is it that we want to gain from this chapter? So we know the why is because they're everywhere, and they're in every engineering system. And the questions that we want to answer is, well, if I have this type of piping system, how much stuff is going to go through it? Imagine that you're pumping through this orange juice or beer or oil. So that how much stuff is very important for you to be able to get some kind of economic analysis. Then the other question is, if I have this piping system, do I need to put in a big pump, a small pump? How much pressure does my pump need to provide? How large should it be? And as a designer, you would be interested in knowing, well, would a 1 centimeter pipe be sufficient to do the job, or do I need a 1.25 centimeter diameter pipe to do that job? Because the financial implications of this question can be significant on large scale projects. So these are all questions that we want to address in this chapter, and as you can see, they break down into two types of problems. One is energetics, is being able to analyze a system that is already there. What if I change my flow rate in my system? How much energy do I need? And the other type of problem is a design problem, where we need to size pipes. We need to see how long, how large, what material it should be for it to be able to carry the fluid from point A to point B at that particular coast. So we want to start with a familiar place, and that would be the energetics of the system. So let's consider this pipe. It's of diameter D and length L. At one end of the pipe, it has one inlet, one outlet. At one end of the pipe, we have flow coming in at a certain flow rate with a certain velocity, gravitational altitude, and working pressure, or that's the enthalpy part that's the flow work part in the enthalpy. And as this fluid goes through the pipe, it can get a boost in energy through shaft work from a pump, and it can have some energy extracted from it by a turbine. And as it goes through the pipe, it's going to leave from the other end, and now it leaves with a new level of energy, pressure Z, V, and if it's single inlet, single outlet, and steady flow, we're going to keep the mass flow rate the same. And if it's the same velocity, if it's the same diameter pipe, we're going to have the same velocity come out as it came in. And along the way, we do have probably have some friction also in the pipe. So the balance between what comes in terms of energy and what leaves has to be balanced by the pump work, the turbine work, as well as the losses in the pipe. So this would be our first law of thermodynamics. What we have just said in words, we can write it, is that the energy balance between what comes in and what leaves will be equal to what the pump and turbine provide, and as well as the friction. So we have written this when we were studying chapter 3 as heads. So here the units of the equation or the terms in the equation are in watts. We can divide by m dot g left and right, and we end up with units of head, which is meter. And here we have our friction. So this whole chapter is really about dealing with this friction type of work. So we know from a balancing type of energetic analysis, we can deduce what is the friction that has been that the fluid has experienced as it went through the piping system. But so if we have everything else in the equation, the pump, the turbine work, as well as all the other energetics of the fluid coming in and out, then that's great. We're satisfied. But what if we're at a design stage? What if we don't have all that information? We want to analyze a change in flow rate in the system, which eventually will change my pump and turbine work in that particular system. How much would my friction change? So the question we want to answer now is, can we find this friction not just through an energetic balance, through a first law analysis? Can we find it from basic principles? So we start asking questions. Would this friction depend on the diameter of the pipe? Maybe. So we're brainstorming now. Would it depend on the type of fluid? So imagine that I am pumping, in instance A, water through the pipe. Would the energetics of the system, would the friction that is produced, everything else being equal, be the same as if I pump honey? Honey is very thick. I imagine not. I imagine that I need much more pumping power to overcome much larger friction in this particular pipe. Would it depend on what material the pipe is made of? Is it rough or is it smooth? What if I have concrete pipe which is rough, and what if I have a different type of pipe? So I imagine that might have an effect. How would the velocity of the flow have an effect also? How fast the flow is going through? Probably. So you see, now if we try to go to basic principles to see what is causing this friction, we start now running into all these multifactorial effects, and this makes our problem actually quite complex, and we will deal with it using the tools that we have learned so far in the class. So the answer to the question, does the friction loss depend on these factors? we can actually find an answer to that by looking at this chart. This is called the Moody chart. And what it does, it plots the friction head loss, the HF, on normalized in a certain way, but this is friction on this axis, against the Reynolds number over here. So we see that the friction head loss, normalized by some flow and pipe parameters, would indeed depend on the velocity in the pipe, the diameter of the pipe, as well as the viscosity and density of the flow that is being pumped. And it also depends on this factor, which is the roughness. So you see we have multiple curves, so each curve is a different type of roughness. So this curve has a roughness factor of this magnitude, this curve has a different, so each curve is labeled. So the answer to the question that we just posed, can we get an energetic analysis based from basic principles? Can we get the friction that a pipe produces from basic principles? So the answer is yes. We see the answer in front of us, and now we want to get through this into more detail. So yes, but how? So let's do some, let's try and analyze the pipe problem, the energetics of the pipe problem. Before we go there, we have, in this chart, we see actually 3 dimensionless numbers. So dimensionless numbers will be used a lot in this chapter. And these dimensionless numbers are the Darcy friction factor. So it's the HF, friction head loss, normalized by a dynamic head and some geometric effect. We have the Reynolds number, which we have seen before, and in this chapter we're going to write it as RED, so it's based on the pipe diameter. So this length scale associated with the Reynolds number is the diameter of the pipe, while the velocity is actually the average velocity in the pipe, which is the mass flow rate divided by the density divided by the area of the pipe. And lastly, we have the roughness effect, the roughness factor ratio, epsilon over d. So all these are unitless, dimensionless numbers, and we will be seeing them repeatedly. The new one here is the Darcy friction factor, which normally we call the friction factor, the F. So it will come later on. Right, so let's try and now work back to our answer. Now that we have answered, yes, it depends on all these, the friction head loss depends on all these factors, what type of fluid, what type of pipe material, and so on. Let's try and analyze that and try and get it from basic principles. So we have our pipe here. Let's consider this pipe that we just looked at. And this is the energy conservation equation, the first law of thermodynamics, with this being our friction head. And now let's simplify the problem. So let's get rid of the pump. We don't have a pump in our system. And we'll get rid of the turbine too. And let's assume that my inlet to the pipe and the outlet are at the same level Z. And I have a constant pipe diameter, which from mass conservation tells me if I'm incompressible, then my velocity at the inlet and the outlet will be the same. So same inlet velocity, same outlet velocity, so they will cancel out, and the same as height between the inlet and outlet. So my energy equation boils down now to the friction is equal to the pressure drop. So remember, this pressure is the flow work part of the enthalpy in your thermodynamics course. So the pressure difference between the inlet and the outlet, it's that stored energy in the fluid that is actually being lost. There is no change in velocity, as you can see. It's mandated by mass conservation, and So the energy that we see lost through to friction actually manifests as a drop in pressure between the inlet and outlet of the pipe. Great. So now we have come up with an equation. The delta P is rho G times HF, the friction head loss. And so we'll call this the delta P friction, the friction pressure loss through a pipe system. So now let's look at that same pipe and of length L and diameter D. And we've already seen from first law of thermodynamics that the delta P is the rho GHF, because only friction is what's eating out our energy. And now let's do, after our energy balance, let's do a momentum balance. So using force balance analysis. And we're assuming that our system is steady. And as you remember, we just moments ago, from mass conservation, the mass flow rate that comes in is the same as the mass flow rate that leaves. M dot in is M dot out. And if I have a constant pipe diameter, the velocity that comes in will be the velocity that leaves. So my momentum fluxes in and out are equal. So I don't have a net momentum a net change in momentum flux between the in and out in the pipe. So that would actually be equal to 0. So our control volume that we're considering for momentum balance is the one shown here. We're taking the inside part of the pipe. So we're taking the liquid inside the pipe. So here it's a cylindrical kind of control volume. So let's see what forces. So if I have my sigma F equals 0 on my control volume, let's see what forces are acting on that control volume. I have the pressure and area here, so P1A, and I have P2 times A, and so the pressure P1 is higher than P2, so it's pushing the flow forward, and opposing that will be the friction force, the wall shear stress. That's the friction between the liquid and the pipe wall. And we have actually looked at this in detail in slide 77 when we were talking about chapter 4. So the friction force will be balanced by the pressure force. And now the friction is due to the shear stress, so it's just the shear stress multiplied by the area. But it is this area that on which the shear stress acts. It's actually the lumen area. It's the wetted area of the pipe, while the pressure acts on the cross-sectional area right here, because the pressure acts perpendicular and compressive. So it acts on the cross-sectional area of the pipe, while the shear stress is parallel and in opposite direction to the flow. So it acts on the luminal area, on the wetted area of the wall, if you will. So we have shear stress here, we have the delta P, and we've already said that the delta P is the rho GHF. So let's plug that with rho GHF. The shear stress acts on the area 2 pi RL. So that's the luminal area. It's the surface area, the internal surface area of the pipe, while the pressure, as we said, acts on the cross-sectional area pi r squared. And then we rearrange this, and we get a relationship between the friction head loss, HF, that's over here, to the wall shear stress. So we find that the friction head loss is really dependent on the wall shear stress. So if I need to find what my friction head loss is, I need to find out what my wall shear stress is. And the rest is properties, geometric and fluid properties. Okay, so that's progress. We now need a way to find the wall shear stress. Well, how do we get the wall shear stress? To get the wall shear stress, you really need to go back to when we derived the Navier-Stokes equation. We have detailed, we talked about stresses in general, normal and shear stresses, and they come from velocity gradients. So the wall shear stress in a pipe is just the viscosity multiplied by the gradient of the velocity at the wall of the pipe. So if I need to get the velocity gradient, what I really need to actually get is the velocity distribution, and then I differentiate it and find the wall shear stress. So we need now to find the velocity distribution in a pipe. And remember, we solved one pipe problem and we found a parabolic velocity profile. But let's revisit that problem again. So here's the question we started with. Is my friction head loss dependent on the pipe diameter? Is it dependent on the type of the fluid? Is it dependent on the wall roughness? Is it dependent on the velocity? And the answer was yes. And now we're halfway in analyzing why that's the case. And we got to the point that the friction head loss really depends on the wall shear stress, which really depends now on the velocity distribution of the pipe. So let's talk velocity distribution. And I skipped this because the velocity distribution we'll come back to this in a second. Depends on the assumptions that you make about your flow. So let's revisit the what we have done in chapter 4 when we solved the pipe flow problem, and we had the assumptions of the flow being fully developed, unidirectional, and axisymmetric. These are very important assumptions, and these assumptions, in other words, now we're going to use for them the word laminar. So in a laminar type of flow, which is all of the above, the flow is unidirectional, it moves in sheets. So you'll see the flow moves in sheets. It has no mixing between the layers or the laminates. Those assumptions can only happen if my Reynolds number, as we have just defined it before, is less than 2,300. So that's what we call a critical Reynolds number for pipe flow. And when we remain below this number, then it's very likely that our flow is going to be laminar. And if my flow is actually above this Reynolds number, my flow becomes what we call turbulent. So the friction head loss depends on the velocity distribution, and the velocity distribution really depends on Reynolds number, whether it's laminar or turbulent. And we have seen the laminar case. We will study both of them now. So this is our laminar case. We found the solution for this type of flow to be the Poiseuille velocity distribution, which is parabolic in R. And we also found, when we differentiated this, we got the wall shear stress, which depended on the velocity, the average velocity in the pipe, the viscosity, and the radius of the pipe. Excuse me, please. Right, and this result applies to in cases where Reynolds number is less than 2,300. In some books it's 2,100. It's not a magic number, but it's in this range. It's not written in rock. It's a guideline number. So great. So now we have found the velocity distribution, we have found the shear stress, and now can we find the HF? So this is what we're after. This is the question we're trying to answer. We want to find the HF, and eventually we want to find the dimensionless HF, which is the Darcy friction factor F. So here's our Darcy. So here's the HF that we're talking about. We want to find this, and here's our Darcy friction factors. Just the HF normalized by a dynamic head, and also a geometric effect, the length of the pipe divided by the diameter. So what is HF? We've already found from our control volume analysis that the HF is related to the wall shear stress, and we now just found that the wall shear stress for a laminar flow that's unidirectional, fully developed, and so on, which is RE less than 2300, is so. So let's take this wall shear stress, plug it up here. So that gives us the HF, and then we'll take the HF and plug it in here, and we get the friction factor. So this is our friction head loss. You'll see the takeaway. It is linear with velocity. The friction head loss depends on the velocity linearly. So if you double your velocity, you're going to get double the friction losses. It's linear with the length of the pipe and the viscosity, but it's actually quadratic with the diameter. So the diameter is a very important factor, which tells you if you cut your diameter by half, you're going to get 4 times the level of friction with everything else being equal. So keep that in mind. And then we can get our friction factor. So you plug it in, and we get 64 times the viscosity over rho VD. And that thing is just our Reynolds number. So the laminar friction factor, the Darcy friction factor, is just 64 over Reynolds number. So keep a mental note on this, and we will come back to it again when we talk about the Moody chart. And now we can solve an example using the assumption of a laminar flow. So they tell you, assume that the laminar flow in this capillary viscometer, which is this particular geometry, it's a reservoir. It's a model for a capillary viscometer. It's a reservoir over here, and here you have a very small diameter pipe. That's why it's a capillary. It's very tiny in size, and that's the whole issue, or the heart of this system is just this small pipe diameter. And the whole thing has a length L. The pipe is of length L, and this length over here is negligible. The height of the fluid is negligible, and it's set out vertically. So what you do is let's say you want to get or to measure what the viscosity of a new fluid is. Let's say orange juice, or maybe oil or honey. You put it in here. You let it drain, and then you collect the liquid in a cup, and you time it. So you can get a mass flow rate, and then from that mass flow rate, given all the problem parameters, you can find the viscosity. So a viscometer is a device to measure viscosity, and it's this simple. So let's see the question that we are trying to answer. Can you relate the viscosity to this mass flow rate that collects in the cup, the m dot over here? Well, let's do some energy analysis. So I will take this as my control volume inlet, this as my control volume outlet, and I'm going to assume that the flow velocity that comes out is very small, that the energy content of it is, the kinetic energy content is insignificant. So here is my first law of thermodynamics. Obviously, I don't have a pump or a turbine. Both the inlet, this is my in, and that's my out. Both the inlet and outlet are open to the atmosphere, so the pressure is maintained atmospheric. And my reservoir here drops very slow, and I'm telling, so that's the inlet, sorry. And at the outlet, we're making the assumption that the kinetic energy is negligible at the end, because the velocity is very small, the kinetic energy content of it becomes very tiny. So the problem boils down to, sorry, that's the H pump cancels out while the friction remains. So the friction head loss is equalized by the gravitational height difference. So HF is delta Z. So we measure the delta Z, which is the length of the pipe, which is L, and we are making the assumption, let's assume that our flow is laminar, which it is. We can always double check what Reynolds number is in the end and make sure that it's less than 2,300, and then we'll make sure that we are laminar. But we found that the laminar friction head loss is so. You equalize it, so you set this to L, and then you rearrange. So we have a velocity which we're going to turn into mass flow rate, and we'll take the viscosity to one side because it's a device to measure viscosity, and we end up with this relationship. Viscosity depends on the density square on the diameter to the 4. So you really need to be able to measure your diameter very accurately. A 10% error in diameter, just 10%, is going to give you more than 40% error in viscosity. So that's very important. And here is your m dot that you measure. So that's how a viscometer works, and it's a direct implementation or application to the laminar friction head loss. Okay, so this is perfect as long as our Reynolds number is less than 2,300. But now, what if my Reynolds number is larger than 2,300? So that's my flow is turbulent. Well, if my Reynolds number is larger than 2,300, then I really need, for me to be able to get the friction head loss, I really need to know what the velocity distribution is. So we need to find the velocity distribution for a turbulent flow. How did we find the velocity distribution for a laminar flow? Exactly, we found it from the solution of the Navier-Stokes equation under the simplifying assumptions of it being unidirectional and axisymmetric and fully developed, and all these assumptions that we have made, which in other words say that the flow is laminar. But when our flow is turbulent, the velocity profile is going to be different, and I would expect my friction head loss to be different. So this is what we want to get. What happens next? How can we compute the friction factor for a turbulent flow? Well, we need the velocity profile.